It's an honor to speak here. So here's my plan. I'm sorry the word was small. So I'll first give a brief introduction to the endoscopy theory. I hope it's accessible to non-experts. And then I will describe an extension problem related to endoscopy theory, which is the endoscopic character identity, and I will specify it later in the talk. And the main tool of solving this problem is the stabilized twisted trace formula, which has been a long project led by Moeglin and Waldspurger, and which has been just recently finished. And in the end, I will just give the idea of how we use this trace formula to prove the endoscopic character identity. Okay. So just to motivate the idea behind endoscopy theory, I will start with the Langlands correspondence, and I will just state it very formally. So here's the setup we need, and we let F2 be a real p-adic field. G is a quasi-split connected reductive group. You can think G as GON or symplectic group, orthogonal group. And we have the absolute Galois group, and also the Wei group, which is the extension of the Galois group if your field is real, and if it's in p-adic case, it's a subgroup of the Galois group with a refined topology. We also define this LF, which is so-called local Langlands group, and it is the Wei group when F is R, and is the Wei group cross SO2C when F is p-adic. And we also need this Langlands dual group we denote by LG, and it's a complex group G hat semi-direct product with the Wei group, and in this particular example, G is equal to SP2N. It's written in this way. Okay, and now we define the set of Langlands parameters, which are G hat conjugacy classes of admissible homomorphism from LF to LG. We also define the set of isomorphism classes of smooth reducible admissible representations. Then the conjectural local Langlands correspondence tells you correspondence between these two sets. And when G is equal to GLN, this has been proved by Harish-Chandra and Annie that this is a bijection. But in general, it's not true. And it is conjectured that the set of parameters will give you a partition of the set of representations. And in particular, for each subset which is parameterized by these parameters phi, they are finite. And we believe that they are L indistinguishable in the sense that they should give you the same L function. Although in general, it's very hard to define these L functions for representations. And I think one of the purposes of the endoscopy theory is really to distinguish these representations in the packet. But for this talk, I want to view the endoscopy theory as a special case of the principle of functoriality. So suppose you have two reductive groups, one is G prime and one is G, and you have L homomorphism from LG prime to LG. Then it induces a map for the parameters from G prime to G. And the local Langlands correspondence predicts a map from the representation of G prime to representation of G. So a natural problem is to find a purely representation theoretic way to characterize this map. And there are two common ways, and one is to study the periods, and the other is to study the relation of the Harish-Chandra characters from these two groups, or its twisted version. So the endoscopy theory will be a special case of this, and the relation between the representation of these two different groups will be expressed through these Harish-Chandra characters. And here I want to be a little bit more generalized, so I'll consider the so-called omega twisted endoscopy. So omega is characters of G, and you can take G to be any quasi-split reductive group, and then in the setup of endoscopy, G pi will be an omega twisted endoscopic group, and the rho is omega twisted endoscopy embedding. And to be a little bit more precise, if you wonder what are these things, So this G prime, if you look at its dual group, it will be a closed subgroup of a dual group of G. And for the L homomorphism rho, it's invariant on the conjugation by S up to a twist. And the twist will correspond to the character omega that you start with. Okay. And so now I want to recall a little bit about this omega twisted Harish-Chandra character. So suppose you take a reducible representation and suppose it is invariant under a twist by omega, then you can have an intertwining operator and you can define this twisted trace. And this gives you a distribution on smooth complex supported functions. And we call such distribution twisted character. And this character can be represented by local integral functions. So this is a theorem. And this function will be conjugate invariant up to a twist by omega. So in this talk, I will refer the characters either to this distribution or these functions. So back to the setup of endoscopy, you want to relate these characters or these functions on different groups, and they are almost conjugate invariant. So the idea is to match the conjugacy class. And in the setup of endoscopy, you have this special feature that you can find maximal torus on both G and the endoscopic group, and there's a natural isomorphism between them. And suppose you have such identification between the maximal torus, then you can try to intersect any conjugacy class on G prime with this maximal torus T prime, and then you map to T. And in some sense, it gives you a matching between the conjugacy class from G prime to G. But you see, the problem is that not every conjugacy class will intersect T prime with non-empty elements. So what you have to do is you have to go to the F bar conjugacy class. So you take our semi-simple G prime F bar conjugacy classes, you intersect with T prime, and you go to T, and that will also give you the conjugacy class of F bar inside G. And although this identification between the maximal torus might not be unique, but it turns out that this map between the conjugacy classes is unique, and well, it's determined by the endoscopic embedding rho. And in fact, this is a map over F. So you can talk about a conjugacy class, F bar conjugacy class defined over F. Okay. And so since you can only match up the conjugacy class of F bar, so you have to to compare the characters. It's not enough to just see the value on a single conjugacy class. You have to, in some sense, you sum the conjugacy class in a bigger conjugacy class over the F bar points, and we take a finite linear combination of characters and we call it stable if over the regular semi-simple elements it is invariant on the conjugation by the F bar points. And so in this talk, I'll also just call this linear combination, finite linear combination of characters as characters, just to generalize the set of characters. So now, once we have the matching between the conjugacy class on G prime and G, we can try to see what's the relation should characterize. So what's the relation on the characters on G prime and G should characterize the map that predict by the local Langlands correspondence in the setup of endoscopy. So if you take a character on G prime and a twisted character on G, and we suppose the one on G prime is stable, then we'll say that the twisted character on G is a spectral endoscopic transfer of the stable character on G prime, if there's such a relation. So this means that delta is any regular semi-simple element on G, and its value, the character takes value at eta is equal to the value given by the stable character on G prime with the coefficient delta, which is the normalized geometric transfer factors. And basically you sum over all the F bar conjugate class gamma in G prime that match to delta through the map that I described in the previous slide. And also there's another way to describe this, because we can also view these characters as distributions. So an equivalent way of describing this is that you can pull back the stable distribution on G prime to a twisted distribution on G by this Langlands Shelstad transfer map. And if you try to expand the low equality by using the Wild integration formula, you can go back to the relation between these character functions. Okay. And so the endoscopy theory will specify for you for which stable characters on G prime and for which characters on G that they will satisfy this relation. So their characters will be related in this way. And for that, we have to assume the local Langlands, or at least we need to know something about the packets on G and G prime. So if we assume a local Langlands, and now this time we take a parameter which is bounded, and invite the local Langlands correspondence, they should correspond to a temporal representation, but that's a technical issue. So we just take a bounded parameter, and we define these two groups, SV and discrete SV. And now if you take a semi-simple element in SV, then you can easily see that your parameters will factor through an endoscopic group, which is determined by S and also phi. So basically, this is essentially how you define this endoscopic group. And once you have this, you can try to see the relation between the packets on G prime and the packets on G. And so the conjecture is that these two packets should be related through the character relation that we have described previously. So the conjecture will be that on G prime, you can find a stable linear combination of characters in the packet parameterized by phi prime. And under the spectral endoscopic transfer, it will become a linear combination of characters in the packet of pi phi. Okay. And for these coefficients, I denote by epsilon pi x. So remember that x coming from S. So x is the image of S in the script as phi. Oh yes, it should be epsilon. Oh, yeah, it should be the same. Yeah. So actually, you can normalize these coefficients so that they can have a nice meaning. So if you normalize in a nice way, then you get inclusion from the representation in the packet to the characters of this script SP, which is a finite group. And in particular, it has become the bijection when F is p-adic. So in this way, you can parameterize the representation in the packet by the characters of this script SP. And a lot of cases has been proved for both of these conjectures. And so in the real case, it's been proved by Shelstad, and also we know these character identities for symplectic group and unitary groups. And for proof of such identity, suppose you have enough knowledge of the characters, then you can try to see whether you can match these characters. And I guess that's how people think of this problem when f is real, because in that case, you basically have the twisted, so you basically have a character parameter. But in the p-adic case, we are far from knowing a formula for the characters. And in some cases, we do know, and we can cook up some package and show this character identity by just comparing these characters. But in general, we don't know, and the proof has to go through a global argument. And people use trace formula to prove such identities. Another remark is that in all these three cases, the group SV is very simple. It's just a 2 group. So it's just several copies of Z2. And because of that, so this coefficient S from pi will take either value 1 or -1. And so in fact, the fact that this group is abelian actually reduces a lot of work. In particular, this coefficient cannot be 0. But in general, this group can be non-abelian, and so this coefficient can be 0. So it will be very strange in the general situation. And such case can happen, for example, so if you take the spin group, so a non-abelian SV will, for example, look like this. So it's a semi-direct product of 2 copies of Z2 with another Z2, and this extra Z2 will act by permuting this to Z2. And yeah, so that's a case that this group is a bit non-abelian. Okay. So that's all I want to say about the endoscopy theory. Now I want to describe a problem which is an extension problem for extending this endoscopic character identity. And the most general setup is if you have 2 quasi-split reductive group, and we assume the field is p-adic, and we assume these 2 groups have the same derived group. And so the quotient will be a torus, and we denote it by D. And for example, you can take G to be SLN and G tilde to be GLN, then lambda will be the determinant map. Also, the main case will be G is the symplectic group, and G tilde is the general symplectic group, GSP, and lambda is the similitude character. And in this case, if you have an endoscopic group for G tilde, then on the dual side, you can map that into LG, and you will get an endoscopic group for G. And moreover, this two endoscopic group G prime and G tilde prime, they have the same kind of relation like a G and G tilde. So they have the same derived group, and if you take a quotient, it's the same torus D. So the natural problem is, suppose we have a character identity. So we know how to relate certain characters on G prime G. Then you can extend these representations on G prime G to G tilde prime G tilde in a certain way, and you can ask whether such a character identity still holds. So that's the problem. So since the character identity is expressed in terms of package, so the first step is you need to build up certain candidates for the package of G tilde and G tilde prime. And to motivate the idea, we go back to the local Langlands correspondence. So there's natural suggestion from the parameters of G tilde to the parameters G. And if you take a parameter of G and take its pre-image, in fact, it becomes X torsor, so this X group will act transitively. and X is also identified with the characters of D by local Langlands correspondence for tori. And the conjecture for the packet of G tilde related to the packet of G is the following. So if you restrict the packet of G tilde to G, you should get the packet for G. And if you twist the parameters of G tilde by omega, then that will be the same as twisting the packet by omega. So from this, it's natural to look at all the representations of G tildes so that the restriction will have. Oh, lambda, yeah, lambda is like a determinant map. Oh yes, it should be omega composed with lambda. Sorry. So to look for the packet for G tilde, you first take all the representations of G tilde so that the restriction has non-empty intersection with the packet of G. And in fact, it has the following two properties. So if you restrict that to G, you end up with the packet pi phi. And the reason is that the pi phi will admit a stable character. The stable character is invariant under the conjugate action by F bar prime, so in particular it will be invariant under the conjugation by G tilde. And also, if you take two representations in this set, and suppose that the restriction on G has a non-trivial intersection, then these two representations are isomorphic up to a twist. And again, this should be omega composed with lambda. So this will give you some idea how you look for the packet for G tilde. But again, in general, because essentially because this group SB can be non-abelian, the structure can be still be very complicated in the general case. But in the main case that we consider in this talk, so G is symplectic group or even orthogonal group, and G tilde is general symplectic or the similitude groups. So the situation will be quite simple. So we first quote the theorem about multiplicity free. So if you take a representation of G tilde and you restrict to G, it is multiplicity free. And it's not true in general, actually. And it has something to do with the fact that this SB group, the squid SB group is abelian. And as a consequence of this theorem, we have the following corollary. So if you take the stabilizer of a parameter of G tilde under action by X, and also you take the stabilizer of a representation of G tilde again by the action of X, then in this setup, these two centralizer groups should be equal. So motivated by this corollary and the previous conjecture, it's not hard to imagine that the packet for G tilde in this case should just be a set of representatives of the big set that we built in the previous slide, mod out X. And once you choose such a set of representatives, then by this corollary, you can span all the elements in this set just by twisting by omega, and again it should be omega composed with lambda. So this will be how you look for these packets for G tilde. And so now we go back to the setup for the endoscopic character identity. So we take a parameter for G, and we take a parameter of G tilde which lift G, and we take a semi-simple element in SV tilde. And as we said previously, this V tilde will fax through an endoscopic group of G tilde. And when you map to LG, you see V will fax through an endoscopic group of G. And in this particular case, because G is symplectic or special even orthogonal, this G prime will be a product group. And this G1, G2 will be also symplectic or special even orthogonal, but of a smaller rank. And it's also not hard to describe the endoscopic group for G tilde. So it is going to be a product of two similitude groups corresponding to G1 and G2. So it will be the subgroup of this product group. And because G prime is a product, so you can assume V prime is a product of V1 and V2. And by induction, we can assume that we know how to we know how to construct the package for G1 tilde and G2 tilde. And then we can define the package for G tilde prime just by restricting the package for G1 tilde cross G2 tilde to G tilde prime. Okay. And once you have the package from the endoscopic group, then it's natural to define the stable character just by summing all the characters in this package. And again, the reason you sum all of them is because that the centralizer group SV tilde prime is abelian. So all the characters should be all its characters should be one-dimensional, and essentially when you take value at 1, it is equal to 1. And by induction, you can assume this is stable, and moreover, when you restrict to G prime, it gives back to you the stable character on G prime. So that's on the endoscopic group side. And on G, you also want to extend these characters to G tilde. And for that, we need the following proposition. So this proposition tells you that if you restrict your X to SV tilde, which is a subgroup of square SV, then those coefficients showing up in the endoscopic character identity will be invariant under the conjugation action by G tilde. Okay, so after you do this, then you can define similar coefficients for G tilde just by using the coefficient for G.
How do you prove that proposition?
Yeah, so in fact, you prove a more general thing. So actually, it's like a special case. You restrict X to this. You restrict X to this subgroup, but if you take the foregroup and you look at its action, so suppose X is inside is split as phi, then they will be equal up to a character. So this will be, so omega X will be a character for G tilde F mod GF to C. Okay, and where the character comes from is from the twisted endoscopy. So for any X as we described before, that the parameter will fax to a certain endoscopic group for G. And if you just pull back, you may not necessarily end up with an endoscopic group for G tilde, but it will always be a twisted endoscopic group. And so this will be a twisted endoscopic group, omega twisted, and the omega will be equal to this omega x. So that's the general picture, and in particular, when x lies in the centralized group associated with B tilde, then you are expecting an endoscopic group showing up here. So the character will be trivial, and this will be trivial. And essentially to prove this, because they come from the endoscopic character identity, so you go back to the endoscopic character identity and try to do a conjugation. So the endoscopic character identity will be a relation between characters on two groups, and one is G, and over G you can conjugate that character by G tilde, and then you can and you can see how this equality changes, and essentially it will goes to a property of the transfer factor that this transfer factor delta gamma sigma, if you conjugate sigma by G, then this character will pop up. So essentially, it comes from the property of the transfer factors. Okay. So now you can define these coefficients for G tilde, and then for any subset of representatives, which we think they will be the candidate for the packet of G tilde, you can always define these characters. So the theorem we want to prove is that you can always make a choice so that the subset of representatives will be the endoscopic transfer of the one that you set up on the endoscopic group. And for the second part, because you prove this by induction, so in the inductive assumption that you have to assume that this the sum of the characters in this packet is stable. So you prove both of these. And there's a remark that in the case of orthogonal similitude group, we prove this theory only module out the conjugate action by the 4 orthogonal similitude group. But you can refine our argument, and I think you can drop that. So now I want to, so this is a theorem, and now I want to talk about the method to prove this. And the main input will be the twisted stable trace formula. So to talk about trace formula, we have to go to the global setup so that K be a number field. And we want to just work out the trace formula for our theorem. So I'll take G tilde to be a symplectic orthogonal similitude group, but these trace formula are quite general, and they are true for all reductive groups. And in this case, we fix a central character on the eidetic points. Then it is well known that this L2 spectrum can be decomposed into a discrete part and a continuous part. And we also take a test function like that. Then we define and operate on the discrete spectrum. And it is a theorem of Mood that is a trace class. So we can talk about the trace of this operator. So the main, I think the main purpose of the stable trace formula is to stabilize the trace of this operator. And what I mean is that you want to express this as a stable distribution, subtract some stable distribution on the endoscopic group. But because that this endoscopic group, so the discrete spectrum on endoscopic group will not only transfer to the discrete spectrum of G, in this case G tilde, but also transfer to some continuous part. So in order to write down a nice formula for the stabilization of this trace, we have to add some continuous part into that. So what we do is we add some symmetric part in the continuous spectrum, and the symmetry is given by some Weld group action, so that this part can still be discrete, even though it's come from the continuous spectrum. So the sum will be a discrete, and that's usually called the discrete part of the trace formula. And then we can state the formula for the stable trace formula for this distribution. And we state it as the following theorem. And it's not just an identity, it's stated in this way. So by induction, one can define the stable distribution in the following way. So basically, you subtract from the discrete part of trace formula by all these stable distribution on the endoscopic group, and you want to show that it ends up with a stable distribution. So the main point of this theory is really to show that something is stable, rather than proving an identity. And from this theory, you already see that this is kind of like global analog of what we want to show in a local situation. We want to compare the characters on G. So in this case, it's G tilde and G tilde prime. And now this discrete part trace formula already contain the characters of G tilde. And also for the stable distribution on G tilde prime, we have a conjecture. So it's a very I think it's a quite big conjecture that you can decompose this stable distribution into pieces, and they parameterized by the so-called alpha parameter. But the main point that is for each segment is essentially the product of local stable ones, local stable distribution, and the stable distribution associated with packets. And here, in the general case, they are associated with alpha packets, but in particular, they will be associated with the packet that we have been talking about in the endoscopic character identity. So in some sense, that the stable distribution on G tilde prime, so this is the global analog of that is already in the formula, and also you have the global analog of characters on G tilde. But because it is a conjecture, we don't know exactly it takes this form. So that if you try to use this trace formula to prove the local identity, in fact, you cannot prove anything, because the left-hand side is always like a black box. You don't know what it is. So you only know that, well, the difference will be a stable distribution. So that's not going to help you approve the endoscopic character identity just from this formula. And that's why we need a twisted one. So for the twisted trace formula, we take a character on G tilde adel, model G tilde k, and just for our purpose, we also model G adel, but that's not necessary in the general setup of twisted trace formula. And then we similarly define a discrete part of the omega twisted trace formula. So the main part will be a twisted trace on the discrete spectrum, and analogously, you add an omega twisted symmetric part from the continuous spectrum. And now we state the stabilized twisted trace formula as an equality. And this time, it's really an equality because the right-hand side will be defined by the previous theorem of Arthur in the stable trace formula. And in particular, for this twisted endoscopic group, they do not include a G tilde. So they will be exactly of smaller rank. And so both sides, it's kind of relating the automorphic representations on one group and some other groups. Okay. And so now I want to explain how we can just make use of this trace formula to prove the local character identity. So just for simplicity, I'll restrict to a very special case. So I assume G is symplectic, and also the local parameter phi will parameterize the discrete series representations. And I let local field F to be the localization of the global field at the place U. Okay. And there are several ideas. And the first idea is that you can take your stable trace formula and split into pieces just according to families of symplectic parameters attached to automorphic representation. The reason you can do that is because these symplectic parameters are really like eigenvalues, and they're eigenvalues by the action by these spherical functions. So in some sense that so you have to split these trace formulas according to the eigenvalue C tilde. And the second idea is very standard. So if you want to prove something by global argument, first you lift the local representation to a global automorphic representation. And this is usually a standard argument by simple trace formula. But in this time, in this case, we can take this lifted automorphic representation and we take these symplectic parameters, and by Arthur's theorem, it will give you a global parameter. So this global parameter so it's very special here, because in general you wouldn't get a global parameter because you don't have a global Langlands group. But in this case, these global parameters can be formulated in terms of generic automorphic representation of GON. So there's a way to get around of that, and you can still think it as like a parameter. And so we'll just use the notation of a parameter for that. And we can further require that if you think the parameter can be lifted to G tilde, and we can further require that the component group of the centralizer of this lifted global parameter is trivial. And that's something very special about this case, and it has a very striking effect, because these groups are like they have local analog. If you have a local centralizer group which is trivial, which means that there wouldn't be any endoscopic contribution. So the package wouldn't have wouldn't be related to any representation of the endoscopic group. So if you look at just the ordinary stable trace formula, then this means that
So how do we ensure that there's such a lift?
yeah.
That you can, or such a
Yeah, so you mean why we can require this group is trivial? Yeah. So the idea behind this is a kind of very special phenomenon for the similitude group of this symplectic group, and especially even orthogonal group. So we know that for these symplectic groups, they can only be split, and there's no other choice for quasi-split groups. But for even orthogonal groups, you can twist by a quadratic character, because there's an action automorphism by this O2n. So you can always add a quadratic character and define an orthoform of these groups. And if you take your G to be symplectic group, then its endoscopic group will be either symplectic group, will be G1 plus G2, and G1, G2 will be a symplectic group, or a special even orthogonal group up to a twist, with a twist. But when you go to the endoscopic group for the similitude group, then that will be a subgroup of this, the product of the similitude group. Usually we define like this. Well, maybe let me just say it is a subgroup of the similitude group of these two. But for this to be endoscopic, both of these has to be split. So this, if this is endoscopic, both of these has to be split. So in some sense, there are less endoscopic group for the similitude group compared with, say, the symplectic group, where you can allow another twist by eta. So that's a local situation, and also the global situation will be like this. So what you're trying to do is, suppose if you look at the symplectic group, the parameter will affect to an endoscopic group like this, and suppose these are all split, which means that if you go to the endoscopic group, well, if you lift to the endoscopic group for the similitude group, you also get an endoscopic group. But when you globalize, you can always add a global quadratic ideal class character, so there's a global twist, so that at this local place, it is trivial. So locally, you preserve this endoscopic group, but when you globalize it, you're adding a quadratic twist. So when you look at the global picture, it's not an endoscopic group. It becomes a twisted endoscopic group, essentially. So that's why when you do such a trick that globally, you don't see a contribution from this group. So it's like you can globalize an endoscopic group for the similitude group such that when you globalize it, it's not an endoscopic group, but it will end up in the twisted endoscopic group. So it wouldn't appear in the stable trace parameter when you look at when you first split the trace parameter according to the syntactic parameters, if you do that. So that's the idea behind this, and I think that's very special for these groups. So in some sense that you can tell whether it's an endoscopic group or not, just look at whether it's a split group or non-split group. And certainly, I don't think you can do this trick, say for like general G, and when you lift to G tilde. What do you mean by global Steinberg?
No, locally somewhere Steinberg.
Why is that?
I don't know. I don't really understand these things, but the image of the local parameter at that one place is then very large in some sense, and there's nothing much that you can commute with it locally at that one place, let alone globally.
Yeah, you don't. Yeah. So the local group can be very large, and the globally I want it to be trivial. So you don't compare it.
No. But if you make Steinberg and you make the image of phi locally at that place large, so you make. I mean, S is something like the commutator of the image of
Yes.
phi dot. So if
It can still be.
It can still be non-trivial.
Because the homomorphism from this local SV to the global one is not an inclusion. So there's really no control of this group by these local groups. So no matter whether it's large or small, then yeah, you model out the component, connected component. So
Image of phi dot sufficiently large at one place. Well, the principal SL2, I guess, is taking the standard. That's not enough, of course. Never mind the set of connected components, just the commutator to be the center of the. Anyway, it doesn't matter.
yeah, I think the philosophy is that when you go to you model out the connect component, actually, even you take all the places, really this group has nothing, has no control on this one. So this map, it can be non-subtractive. Well, pardon? Well, first the local one will map to the global one. Oh, wait. Well, if it's globally, it's a centralizer, then yeah, it's the other way. But because you model out the center, there's really you don't know how this map behaves. Not going to be inclusion. So that's why it's. But to play this trick, you don't really have to look at this local component. You just play with this to see how it affects the endoscopic group, and then you just globalize it, and you're adding this outer twist, and then you move this endoscopic group to the twisted endoscopic group. So the impact of that is that when you look at, so the first line will be the stable trace formula, and then it will be equal to the stable distribution for G tilde, and there's no contributing from the endoscopic groups. And also because you take pi dot to be in the discrete spectrum, so the discrete part will be essentially given by the discrete trace of the discrete spectrum. And if you look at the twisted trace formula, also because of that fact, that either this twisted distribution will be 0, or there's only one twist endoscopic group will contribute. So if you look at these two formulas, we are in a good shape of proving the local identity. So suppose this d tilde, so remember that this stable distribution S can be decomposed into global packets, and suppose C tilde will determine a single packet, then the first equality just shows that the local packet should be stable, and the second formula tells exactly the endoscopic character identity. So if there's only single global packets in this distribution, but unfortunately we don't know that. So this is like a difference between the similitude group and the symplectic group. So we say that these symplectic parameters may not determine these global parameters uniquely, or you say that there could be several global packets which share the same symplectic parameters. And in other words, you can find a character which, after twist the global packet, you get different global packet, but for almost all places, they are the same. And because for our purpose, we want to prove the local identity, so we want to single out the local packet. So we don't, it's not necessary to single out the global ones. So it suffices for us to put this weak condition that if the global packet is so if it's fixed for almost all places except U, then the global packet will be fixed by omega prime. And the way you achieve this is when you lift your local representation to global representations, you can very carefully choose a finite set of places. And for those finite set of places, you require the lifted representation to be in the temper spectrum and also to be spherical. And then for this to be satisfied, you just need to stay away certain closed subset from those tempers. You look at the temper spectrum over those places. And so by result of seeing that you can always take open set in the temper spectrum on a finite many places, and you can lift your local representation to a global representation so that on those places it will lie in those open set that you choose. So that's how you can impose this condition, and this condition suffices for you to single out the packet at U, so that you can go back to these two equalities and to prove the local results. So yeah, I end up here.